All right, so as you, oh, I'm gonna have to do it on another screen here. So as you find that worksheet, if you're having trouble locating it, let me just give you some help here. So we'll switch to share. All right, so from the bulletin board page, you go to topics, and then unit 7. And then over here on the right is where I'm keeping all the worksheets and stuff. This first segment, we've done all of those. That's all circular motion. And if you're still needing some review, if the concepts about circular motion, uniform circular motion, centripetal force, centripetal acceleration, if you're still a little bit confused, need some review, there is a nice screencast and PowerPoint right here. Centripetal acceleration screencast, centripetal acceleration PowerPoint. That'd be a good way to review, is to watch that presentation by Ms. Turk and the associated PowerPoint. I don't use that PowerPoint, and I teach it with a little bit different material, but it's the same concepts taught from a different perspective. Always could be helpful to hear someone else's teaching style. And then right below that, you see rotational kinematics screencast and rotational kinematics PowerPoint. Today, we're going to be starting rotational kinematics. That's where we're switching gears to. So we're just kind of working our way down this column. And if after today's lesson, you still think, especially if you haven't learned a lot about radians and things like that before, you may feel like, you know, I still don't feel super confident in this. Watch this rotational kinematics screencast. She spends a little bit more time talking about what a radian is and how it connects. And she takes a little bit of a different direction in the way she introduces these concepts. Very good, very well done. So again, just hearing another teacher's perspective, another approach can be helpful. And then this one is the one we're looking at. So right underneath that screencast is rotational kinematics worksheet, number 1, graphical analysis. So that's the worksheet that you want. If you click on that, you should see this. And this should look in format vaguely familiar. This is a lot like what we did first semester with linear movement. So towards the end of the period today, we'll be working on this worksheet, but I wanted you to go ahead and just see if you could find it and download it while we were getting attendance recorded. So let me go back to the notes now. So hopefully everybody's able to find that okay. Just a quick reminder before we jump into the introduction for rotational motion. Those videos on AP Classroom can be extremely helpful. I would say that this unit, which is unit 7 on Axis and also unit 7 on AP Classroom, is probably the hardest unit of the year for most students. And it's the second half of unit 7 for us, but it's the entire unit 7 for College Board. It's actually units 15 and 16 on positive physics. So if you look at those positive physics quizzes that are coming due, the unit 10 assessment on positive physics is due Monday, and it is on uniform circular motion, what we've already finished, what we've just wrapped up. And then units 15 and 16 on positive physics are about rotation that we're starting today. So it's all about this unit 7 on Axis, units 3 and 7 on AP Classroom. I know it's a little bit confusing about having all these different units. I'm actually tempted to just change my unit numbers to match College Board at least next year, but I don't really care for some of the order that they cover things in, so I'm hesitant to do that, but maybe I'll just still cover them in my own order and give them a different number to match so it's not quite so confusing. But anyway, that's the outline and the order for what we're doing right now. So any questions on preparing and completing those quizzes while we're just reminding you of that today? All right, hopefully it's clear. I know some people are already done with unit 10, and that's good. You don't probably want to wait till Monday. If you haven't started yet, I'd get started. I'm not giving you any new assignment today, so just keep working on those quizzes. That's what I want you to be focusing your out of class time on. That and potentially watching some of these daily videos to help make sure you're learning the material well. All right, so this set of notes today is actually, this PowerPoint is actually provided by the publisher of your textbook. And so it will follow the flow of your textbook a little more, and it's a reminder for me to encourage you to be reading in your textbook. So we have finished up units, I think it's unit 9 in your book for the uniform circular motion, and now we're moving into units 10 and or chapters 10 and 11 in your textbook. And today's notes will be on the majority of chapter 10. Next week we're going to wrap up chapter 10 and also cover chapter 11. And then the week after that will be just anything we don't finish in chapter 11, we'll finish up and just be practicing problems and finishing things up. You can see in the outline for chapter 10, we're going to start with the discussion of the concept of the radian. And that's why I was saying, if you understand what radians are from your math class, it should be pretty easy today, this part, and you'll just kind of skate right through that. If you don't really know what radians are, we're going to try to explain today, but if it's a little too quick or you just need a little more detail, watch that screencast that I highlighted that's there on Axis. Then we're going to talk about rotational kinematics, and that's what we're going to cover today. Then we're going to talk about torque, inertia, and other rotational dynamics next week. Okay, that'll be the focus next week. But today we're going to get through radians and rotational kinematics. And you can see this picture on this slide. They're showing an ice skater. And if you've watched much ice skating, you'll notice even here as this woman is spinning in the air and in one of her jumps, she's got her arms crossed. And you'll notice, like with divers, when they're doing flips and twists, if they're doing twists, they tend to, pull their body in really tight so they can twist rapidly. And there's a reason for that. We're going to actually learn the physics behind why when a skater has their arms outstretched, they rotate more slowly. And as they bring their arms in, they speed up. They're not doing anything magical. They're capitalizing on physics. When their arms are outstretched, their mass is more spread out. And as they bring their arms in, their mass is more centrally located. And they naturally spin faster because of physics, not because of some special technique they're using. So we're going to learn all the background of why that works in this unit. But first, we need to make sure you understand the difference between what we've been learning and what we will be learning. And that is often referred to as translational versus rotational motion. So everything we've studied so far this year, even including the uniform circular motion that we just finished, all of that has been translational in nature. The objects we have been talking about have been moving from point A to point B. Sometimes they moved in a straight line. Sometimes they move in a circular path. Sometimes they moved in curved paths, stopping and starting. But they were all, the center of mass was moving from one position to a new position over time. And that is what we've studied this whole year so far. However, that is not the only kind of motion. So, and this animation just kind of shows you that it doesn't necessarily have to be in a straight line. But hopefully you notice on this animation that it never rotated. The orientation of that object stayed the same. It did not spin in any way. The center of mass just moved on this unusual path. All of that would be considered translational. The center of mass is moving from one position to another on whatever path it chooses, but the object itself is not spinning. Okay, that's what we've focused on so far. What we're going to be talking about now is rotational. What if instead of that object moving from position to A to position B, what if instead it's just spinning around its own axis? Well, that is rotational motion, and there's a whole different set of equations we use for rotational motion. Now, along this year so far, you've heard me talk about there's a lot of equations we're going to learn that College Board doesn't give you on their formula sheet. Today is going to be an exponential growth of that. You're going to have 4 or 5 different equations just today that they don't give you, and you're going to see in the notes. So you'll want to be copying some of these equations down, some of these definitions down into your notes, because they're not on here. And if you have been keeping a collection of those equations somewhere, like I've suggested maybe even at this bottom part of the AP handout where you got a big blank space, or if you've just been putting it in a particular place in your notebook, I would encourage you, and I'll remind you as we go, hey, this equation isn't on that sheet, so you need it or you could need it. And many of the rotational equations are not given. In fact, if I do a quick glance here, there's 2, I think. There's some down here that we're going to learn next week, but of all the ones we're going to learn today, only 2 of them are on here, and we're going to probably see a dozen. Now, some of them aren't that helpful. They're more baseline to help you see some connections, but there are some that are extremely helpful, and those are the ones that I'll highlight and say, hey, this one you probably want to write down because this one's really beneficial. Okay, so that's what we're covering today is what about this object that's rotating? Now, after we get comfortable with this, then we will move on to the next phase where not only will we consider the object as it rotates, but we will also consider it as it does both rotation and translation. So like throwing a curveball. You throw a curveball that's going from your hand to the catcher or your hand to the batter's bat. And the ball is spinning also. So it has both kinds of motion. If you throw a football, you got the spiral spinning rotational motion as it goes from you to the receiver, hopefully not the defensive back. All right, so those kind of, you hit a golf ball. The golf ball's spinning through the air. Hopefully it's not spinning in such a way that it slices or hooks away from where you want it to go. So the spinning motion is going to be the new added thing, but we will continue to talk about the translational as well. So any questions about what we mean by translational versus rotational? You'll hear me use those words. Sometimes I'll refer to it as translational. Sometimes I'll refer to it as linear. Most of the time, those things are the same. Translational is actually, though, a little bit of a better word because linear, you might infer that it is only moving in straight lines. But we aren't necessarily always moving in straight lines. We know about circular motion now, and even curves. Now that we know that curves follow circular motion patterns, we actually can address all those things. Straight lines, curves, circles, we have all that in our tool belt now. All right, so here are some key variables and vocab terms for this unit. You want to make sure you get these 3 things written down. You'll notice they are not entirely new. The first one is displacement. We've learned displacement, but now we're adding the prefix word or front word. I guess it's not really a prefix, but the first word, angular, to it. And when we talked about displacement, when we were looking at translational motion, most of the time we called it d for distance or x for displacement. But now we're going to talk about it as theta. And we've used that theta symbol before when we were talking about, for instance, the angle of a projectile. But we're going to define it instead of angles in degrees, like we've been defining it. We're going to switch that definition to, instead of degrees, using radians. So angular displacement, not just moving from point A to point B, but how far did it rotate? Did it rotate 30 degrees, 90 degrees, 180 degrees? How far did it rotate? How much did it rotate in angle? Then the second one has got this funny W shape, which is the term omega. So we got theta and now omega. These are all Greek letters. The omega, that funny W, is for angular velocity. And just like displacement is just change in position, we're just now talking about change in angular position, change in how much it moved in degrees or radians. Angular velocity is still going to be velocity. It's still change in position over change in time. But instead of change in position measured in meters, it's going to be change in position measured in degrees or radians, specifically radians. Right now, I'm just using degrees for those of you that may not be too comfortable with radians yet. And then the third one is the symbol alpha. It kind of looks like an A, and depending on the font and the printer and the screen and the document, it may look more or less like an A. When I draw it on the whiteboard, or when you see me write it, it looks more like a fish. So I think it'll let me draw here. So when I draw it, I just draw it like that. That's my alpha. And so if you see me writing that, that's my alpha symbol. And if you're handwriting it, you can see it's sort of similar to what you see here on the screen. That's my alpha symbol, in case you see that on anything that I write. And just like regular translational acceleration, is change in velocity over change in time. This is also going to be change in velocity, but change in angular velocity. So it's going to very tightly connect to all the kinematics we learned first semester, but there is going to be a bit of a difference. There's going to be a slight twist, right? Because we're never measuring any of these in meters or meters per second or meters per second per second. Now we're going to be measuring them in radians or radians per second or radians per second per second. Okay, so we're shifting from a linear measurement to an angular degrees or radians type measurement. All right, so let's break down, first of all, what do we mean by radians? And for some of you, this is review, you got this, it's old hat. For others, you may only know, hey, I know there's a button on my calculator for radians, but other than that, I don't really know anything else. And that's okay. You actually don't need to know a ton about radians, but you need to be at least familiar with it enough to be able to use it accurately. So I want you to have some background into why we use it and how we know what it is. So the reason we don't use degrees, first of all, for this kind of work, when we're talking about projectile motion and it's launched at an angle, degrees is fine because we're just going to use trig. We're not really going to use trig the same way now. We're going to be thinking more about the geometry than the trig. And so if we think about degrees, a full circle is how many degrees?
360.
360. And 360 has nothing to do with a circle other than the fact that somewhere, sometime in history, we've decided that's what it's going to be, 360. It actually has nothing to do with the geometry of the circle at all. It's just a random number chosen sometime historically. And there's debates as to whether it was Babylonians or Hebrews or Asians in different countries, all kinds of different theories. And no one really seems to know where it started, but it isn't anything about the geometry of a circle. The reason radians is valuable is radian is actually defined based on the geometry of a circle. To find radians, the angle, the theta in radians, we take the arc length that's covered as we rotate a certain number of, or a certain angle. We take the arc length divided by the radius for that angle, and that tells us the angle in radians. So instead of being just made on or based on a random number, it's actually based on two things we can measure for a circle. And no matter how big or how small the circle is, if you rotate through a certain angle and you measure the arc length and you measure the radius, the ratio between those two things will always tell you the number of radians. That's where the definition of radians comes from. It's the ratio of the arc length to the radius. Now, this equation can be very helpful. And this equation is not on the AP formula list. So knowing how to calculate the angle in radians might really help you solve certain problems, but they don't tell you on the handout how to do that. So I would put this equation in, that to find the angle in radians, you take the arc length measurement. Sometimes I'll use S, sometimes I'll use D for distance. Mostly it's usually S or D. Occasionally it's X, but usually they use S or D for arc length. I'm not sure where the S comes from for arc length, but sometimes they'll use D for arc distance. And then the radius. So arc length divided by radius always gives you the angle measured in radians. Now, as we start relating these measurements, these angles, and these velocities that are angular in nature to the linear or translational counterparts, you're going to see why this geometric connection makes a difference, why this is so much more powerful. If we use degrees, a lot of the connections we're going to learn wouldn't work. But if we use radians, they do. All right, so that is where radians come from. It's literally the ratio of the arc length to the radius. So here are just a few examples. Since we're talking about rotation, we're going to go around the screen in clockwise order. So we're going to start up at the top left. That's just the same slide we saw in the previous one, same picture we saw in the previous slide, that the angle in radians is the arc length divided by the radius. Now on the next slide, they're showing us if we found that this arc length of 90 degrees, if we measured that arc length, then it was 0.5 pi times the radius. That's how we can calculate that arc length. If we do take 0.5 pi as the arc length times the radius, that's the arc length, and then divide it by the radius, you can see the radii cancel. The radius in the numerator and the radius in the denominator cancel. And we're left with 0.5 pi. Now this may start ringing a bell if you've done unit circle. What is 90 degrees in radians?
Pi over 2.
Pi over 2. I hear a few people saying it. Good. Pi over 2. Well, pi over 2 is the same as 0.5 pi, right? Half pi is pi over 2. So if you know unit circle, then this jump to radians is not going to really be a big deal for you. In the second example, this arc length would be pi times the radius. And if we take pi times the radius divided by r, the r's cancel. And so this angle would be pi radians. And again, if you learned unit circle, you know that 180 degrees is pi radians. So it's kind of proving what you probably, most of you have already learned, but helping you see the measure in radians instead of degrees. So in conversation, sometimes I will say, hey, it rotated 90 degrees. And you'll need to know, oh, that's pi over 2 radians. So there's really only 3 angles that you need to be comfortable with for our class. You need to know 90 is pi over 2. You need to know 180 is pi radians. And you need to know 360 is 2 pi radians. If you know those 3 values, then you're pretty set. If you know all the rest of the unit circle, great, but you really won't need it much. You mainly just need 90 degrees is equivalent to pi over 2 radians. 180 degrees is equivalent to pi radians. And 360 degrees is equivalent to 2 pi radians. However, more often than that, we will be doing, like, again, we're moving clockwise around here. So now we're down in the bottom left corner where the red font is given. Most often, we'll actually be making our measurements in meters or some other metric measure, centimeters, millimeters, something like that. So if we have a circular path and the arc length is 3 meters and the radius is 5 meters, to find the angle in radians, we just still take arc length divided by the radius. And 3 divided by 5 gives us 0.6 radians. Now I want to, especially with this slide and that fourth example, if we look at this 3 meters divided by 5 meters, 0.6 makes sense, right? But what should the units be? If we have meters divided by meters, should have no unit, right? And if you're taking meters divided by meters, they cancel. So there shouldn't be a unit. So here's the sort of trippy thing. We talk about radians and we say, oh, this is the angle in radians. But technically, radians aren't even a unit. Because to find radians, by their definition, you're taking a measurement of arc length divided by a measurement of radius. And those two measurements have to be in the same units. So it is technically a unitless measure. So when you learn about radians in math, it makes sense. We define it. You take the arc length by the radius. You call it radians. That's great. But one of the things you're going to have to start to understand now is technically radians are unitless measures. It's not in meters. And so when we see radians written, there's a reason we do it. We write it so that we can make it clear we're talking about rotational motion and not something like frequency that we're going to be learning later this year. But I do want you to understand that it is unitless, and that's going to be important as we start solving bigger problems later in this unit. Any questions about radians before we start moving on to new info? All right, so for those of you that have had Algebra 2 and you've gone through unit circle, you don't do unit circle in geometry, I don't think. I think it's not until Algebra 2. So, but if you've had that, then this should be pretty much review. All right, so now let's get back to those 3 key vocab words: angular displacement, angular velocity, angular acceleration. We'll start with displacement, just like we did with linear kinematics or translational kinematics. Start with displacement, build it up to velocity, build it up to acceleration. But we're going to do it in one day instead of a couple weeks. So in less than one day, we're just going to do it in about 15 minutes. So angular displacement would be delta theta. Delta theta is the change in angular position. So if we look at the picture here, we are measuring a certain angle And you can, usually in math, we go around the circle counterclockwise, right? We start at 0 and we go counterclockwise around to 360 or counterclockwise around to 2 pi in radians. You can go either direction in physics. Normal is just like math. Normally, positive is in the counterclockwise direction. But you can define it however you want. Just like we can say, hey, normally upward is positive and downward is negative, but maybe for a certain problem, we want to flip that and say, yeah, for this problem, I'm going to make up negative and down positive. That's fine. So here, they're actually rotating in the clockwise direction, even though normally we tend to go the other direction. So don't get too tripped up by that. But they're rotating to a certain spot and they're saying, okay, our starting position is right here. We're not at the 0 position. We're at some other position rotated clockwise from that 0 position. That's our initial position. Now, if we have the object rotate from there to a new position, it will have rotated through a certain number of degrees, or as we're learning now, a certain number of radians. By the way, you will need to use that radians button on your calculator now for a lot of these calculations. And so if you don't know how to switch degrees and radians, on the TI Inspire, it's really easy. Up in the top right-hand corner of the TI Inspire, you'll see DEG for degrees and RAD for radians. Only one of them is showing. If you use the trackpad and click on it, it switches to the other one. So it's really easy. As long as your software on your TI Inspire has been updated, it's an easy switch. You just click, if it says DEG, click it, and it'll change to RAD. If it says RAD and you need to go back, click it, it changes to degrees. All right, back to this example though. We have an initial position and a final position. So finding the delta theta, finding the change in position is literally the same as finding the displacement in translational motion. We just take the final minus the initial. So here is another equation. I don't necessarily think you need to write this one down per se. I mean, I think this is probably pretty straightforward. Final minus initial is pretty much how we do all of our changes. But I do want you to make sure you recognize that while it technically is a unitless value, we're going to use the unit radians so that we understand we have not measured this in degrees. Just to make it very clear that we have measured it using the radians concept. All right, any questions about angular displacement? Instead of how far from A to B in a straight line, how far did it rotate? How many radians did it rotate? All right, let's move on to angular velocity. So again, this is that omega symbol, that funky looking W. The average angular velocity is the angular displacement divided by time. So that's the same definition as translational in terms of it is displacement over time. So if we are going to follow the same pattern, we need to just think about, well, as it's moving from position 1 to position 2, it has an initial and a final angle, and it has an initial and a final time. So to find the velocity, we just need to take the final position and its angle, minus the initial position and its angle, final time minus initial time, and our omega will just be change in position over change in time. Now this equation is not given, and it is really the same relationship as velocity in translational movement. It's just change in position over change in time. But the symbols look very different. So this is one that it is not given on the AP formula list, and it's one that I think might be helpful for you to have as a reference. Maybe you are grasping everything we're talking about very well, and switching the variables around doesn't confuse you. And you can say, well, it's just velocity equals displacement over time. And if that's where your brain is at, great. You might not need to write this down. But if you're looking at this and right now you're still just seeing a bunch of weird shapes, it might be helpful to write it down until you get more comfortable with this concept. It is just velocity. Therefore, it is just displacement over time. But it is angular velocity. So in that displacement, it must be the angular displacement in radians. Questions about angular velocity? All right. The units here will be radians per second. So again, even though technically radians are unitless, we use them here to make sure we know that it's not just like the frequency of something going around a circle, but instead it is actually how many radians it's rotating per second. So we're making sure we don't get it confused with hertz. Okay, we're wanting to make sure we know, hey, this is not hertz, it's not just per seconds, it's how many radians it rotated in a second. All right, now here is something that's often a little bit confusing at first, but then once you see it, it's like, oh, okay, that makes sense. So the omega, that angular displacement, is the same everywhere, but the linear velocity is not. So I'm going to switch the share here for a second. And I'm going to show you an animation to help you visualize this. All right, so on this little animation, you can see we've got a ladybug and an ant. I'm going to move the ladybug out here so it's in the same kind of line as the ant. Move the ant and move the ladybug a little bit closer to the center. So up here you can see it's going to talk about the linear velocity for the ladybug and the rotational velocity, the linear velocity and the rotational velocity for the ant. And I'm going to just be able to switch the speed here by dragging this up and down. So you can see it's actually calling it degrees per second instead of radians, just I think to make it a little more familiar. But we're going to change that rate that it's spinning. So if I click go, they both start spinning. And you can see that when the ant goes one full circle, so does the ladybug. And if I stop it here, we're at 3 o'clock basically on the clock. If I let it rotate around to 9 o'clock, it just went half a circle, and they both went half a circle, right? They both went 180 degrees or pi radians. Now, which one went further though? Well, if we watch their motion, the ant has to cover a lot more ground in terms of how many centimeters it's traveling. To make this circle, the ant has to go a lot further in centimeters. So if you look up here, the ladybug's linear velocity is 10 centimeters per second. The ant's linear velocity is 44 centimeters per second, but their rotational velocity is the same, 55 degrees per second. They're spinning at the same rate angularly, but they're covering different distances linearly. So hopefully you can see that pretty clearly with this animation. If we speed it up a little bit, it becomes, I think, even more apparent that not only is the ladybug covering a shorter distance, the ladybug is going a slower linear speed, whereas the ant is covering a greater distance and therefore traveling at a greater linear speed. But angularly speaking, they both go through the same number of degrees, therefore they're going through the same number of radians every second. So their angular velocities are identical. We can also see the difference in their linear velocities if we graph them. And if we show both here, you can see we've got a circular type of movement, so we get our sine wave type shape. And you can also see that the amplitude of the ant is much larger. Its change in vertical position is much greater than the change in vertical position for the ladybug. So hopefully that helps you sort of visualize what we're trying to demonstrate here. So we'll back to the notes. That the omega, that angular velocity, is going to be the same no matter where the object is on the rotating device, but the velocity won't be. So now we're going to prove it mathematically. So if we rotate from the original position to the new position, it just rotated through 90 degrees or pi over 2 radians. And if we think about putting some numbers on here, so the angular velocity is change in theta over time. The linear velocity is change in arc length over time. If we measure those values, the arc length in this case is 0.4 meters, and the radius from the middle to where that object is 0.255 meters, and the angle is 0.5 radians, or a pi over 2 radians. So if we plug those values in, we can see the angular velocity is 0.5 radians divided by 2 seconds, or 0.25 radians per second. That's how fast it's moving in an angular velocity. In a linear velocity along the arc length, it's traveling 0.4 meters every 2 seconds, so it's going 0.2 meters per second. Now, if we switch that object and slide it all the way out to the edge of this rotating disk, and we still want to make it go at the same rate, we still want it to go 90 degrees in 2 seconds, or in other words, pi over 2 radians in 2 seconds. But now, its position is different. So the radius is no longer 0.255, it's 0.509. It's about double. And instead of 0.4 meters arc length, it's now 0.8 meters arc length. So if I use these new values, I can see that the angular velocity is still 90 degrees or pi over 2 radians per 2 seconds. It's still a quarter of a radian every second. That didn't change, even though it's much farther from the center. The linear velocity did change. Instead of only being 0.2 meters per second, now it's going 0.4 meters per second. And I want you to notice that these are double. We doubled the radius, and then we've doubled the velocity. But the angular velocity is constant. It's still going through the same number of degrees or radians every second. So I'm sure most, if not all of you, have ridden on a merry-go-round. And I remember when my kids were young, I have 2 daughters, and they were probably about 3 and 4 years old. And they used to love to go to the park. And my younger daughter's a little bit more of a thrill seeker. My older daughter's a little bit more cautious. And they're on this merry-go-round, and my older daughter's kind of hanging on tight, and she's enjoying it. My younger daughter's hanging on, and she's going, faster, daddy, faster, daddy. And so I'm spinning the merry-go-round, and I keep going faster and faster. And, I was just thinking about, hey, my kids are having fun. I wasn't really thinking about physics at the time. And and my children, obviously, at ages 3 and 4, didn't know much about physics. So my younger daughter, she's faster, faster, and then she starts clapping and lets go. And as she lets go, she goes flying off the merry-go-round, and then daddy's no longer a good guy. Now she's crying, why did you do that, daddy? There's a difference in where you're at. My older daughter was all the way into the center, hanging on tight. She wasn't going to be flying off that merry-go-round. My younger daughter was out on the edge, enjoying the thrill until she let go. And then it was no longer any fun. So it matters where you're at if you're talking about your linear velocity. My older daughter was close to the center, and while they were traveling at the same angular velocity, my younger daughter was definitely moving faster in her linear velocity. All right. Angular velocity is the same everywhere on the disk, but the linear velocity increases with radius. So hopefully you get that concept. You may even want to write those 2 sentences into your notes, because that fact that the angular velocity is the same everywhere is kind of one of those pivotal facts when you're solving problems. When you're thinking about 2 different objects on the same rotating device, if you remember that their angular velocity is the same no matter where they're at, that simplifies so many problems. But at the same time, you have to keep in mind the linear velocity is not the same. It increases with radius. So if you remember those 2 facts, that can make problem solving for a lot of these questions much, much easier, especially the first statement. The angular velocity is the same everywhere on the disk. All right, any questions? All right, moral of the story, don't let Mr. Webb push you on a merry-go-round. You might get hurt. All right, now let's show a mathematical connection between the linear or translational velocity and the angular velocity, and how it connects to the radius. So these are the 2 definitions or formulas we have. Angular velocity is change in theta over time. Linear velocity is change in position over time. But if we're talking about the same object, the time would be the same. Whether we're referring to the angle or the distance, they would both be rotating, or both times, both situations, both considerations, the time would be the same. If it's rotating 90 degrees in 2 seconds, it's also rotating through that arc length in the same 2 seconds. So if we solve those 2 equations for time, knowing that time is the same for any given object, we can set them equal to each other, and now we can start finding a deeper relationship. So that change in theta over change in omega is going to be equal to the arc length divided by the average linear velocity. And these little AVs just mean average. All right, now if we rewrite this equation and solve it for V average, I'm just multiplying both sides by V average, dividing both sides by delta theta, multiplying both sides by omega, just rewriting it algebraically to get the V average isolated. Now the reason I want to do that is because I know, based on the definition of a radian, that delta theta is equal to the arc length divided by the radius. That's actually how radians are defined. And so as long as I'm measuring in radians, this is true. If I'm measuring in degrees, this is not true. Okay, so it has to be in radians. That's because radians are based on the geometry of a circle. So as long as I'm measuring in radians, that angle change will be the arc length divided by the radius. That's the ratio that defines it. Now, if I just do a little algebra here, first I'm recognizing, well, that arc length, sometimes we use S, sometimes we use D. I'm just going to switch it to D so we have some consistency from one side to the other. It's both arc length, just two different variables. And then if I solve that for R, the radius is the arc length divided by the change in angle. And if we look at these two equations now, on the left, I see d over delta theta. On the right, I see d over delta theta. So now I can substitute in for R, or substitute R in for d over delta theta. And so this relationship is powerful in connecting the linear velocity to the angular velocity. And this is another equation the College Board does not give you. But it frequently helps you solve problems. That linear velocity, its average linear velocity, equals the radius times the angular average velocity. Now, just to kind of summarize and make sure you're not missing the point, it looks like here, oh, if we just take the radius times the angular velocity, we get the linear. That's true, but we could also use it the other way. We could also convert linear to angular just by dividing by radius. So don't lose track of that fact, that we can actually convert either direction from V to omega or from omega to V. And often that's the little linchpin that helps you solve a problem, is they may give you a bunch of linear values and you can find the V using kinematics from first semester. And once you find the V, you just divide by R, now you know the angular. All right, so that's where that connection is going to be in a lot of the more complicated problems. But this equation is not given on the AP formula list. All right, let's wrap it up with angular acceleration. So acceleration, when we talk about translational motion, is change in velocity over change in time, right? How much does the velocity change per second? That's why it's meters per second per second. Well, the change in angular velocity is just going to be delta omega, and change in time is just going to be delta t. So the change, or the average angular acceleration, is just going to be the angular velocity's change over time. And so just like we looked at before, if we have the object rotate through a certain angle, it will be rotating at a particular angular velocity. And if we know what the final angular velocity is, we know what the initial angular velocity is, and we know how long it took, we can find the change in angular velocity with final minus initial. We can find the elapsed time with final minus initial. And we can then find the angular acceleration by taking that angular velocity over time. This equation also not given on the AP formula list. Right? Now, it is just change in velocity over change in time. So if you have a really cemented concept in your brain that acceleration is change in velocity over change in time, then you should be able to think this through. But if this is still sort of just looking like a bunch of symbols and variables, you may want to write this down because this is not provided, but it is a helpful equation. Now, this unit would be radians per second squared. So linear acceleration is in meters per second squared. Angular acceleration is in radians per second squared. A little trivia here, trivia question, see if you're paying attention. What's the third acceleration we've learned? Centripetal. So we now have three kinds of acceleration. Linear, which is change in velocity over change in time. Angular, which is change in angular velocity over change in time. And then centripetal, which is caused by a centripetal force. And we usually measure it in newtons per kilogram. All right, so a little bit of a wake up here. We've got three kinds of acceleration. You have to be really careful about which one you're solving, because linear acceleration is delta v over delta t. Angular acceleration is delta omega over delta t. Centripetal acceleration is v squared over r. They all mean something different, and they all are calculated in different ways. All right. The only one that's on the formula sheet is the centripetal one. The others are not there. All right. Questions on acceleration? All right, let's see if we can find a similar relationship between the linear and the angular versions. So the angular version of acceleration, delta omega over time. The linear, delta v over time. Same thing, if we're talking about a single object, they would rotate and move linearly in the same amount of time. The time can't be different if it's the same object. So if we set them both equal to t, we can set them equal to each other because the time would be the same. So now we've got delta omega over the angular acceleration. And we've got delta v over the linear acceleration. Now, just like we did before, we're going to solve this for the linear acceleration. And then we're going to see if we can find a relationship. Well, we know that if we have delta v over delta omega, we just learned on a couple of slides ago, delta v equals the omega times the radius. That's what we figured out last time we did one of these little derivations. The delta v equals delta omega times radius. So if we substitute delta omega times radius in for the delta v, the omegas cancel, and this simplifies to r. So the delta v, the change in velocity over the change in angular velocity, is equal to the radius. Therefore, if I know the angular acceleration, I can multiply it by the radius and get my linear acceleration. The same exact pattern we saw for velocity, that the radius connects the two mathematically. And this is yet another equation that College Board does not provide. Again, just to sum it up, to convert linear acceleration of a point that's moving in a circle of radius r to angular acceleration alpha, use a equals radius times alpha. So you can use that relationship to convert a to alpha or from alpha to a. You can go back and forth from linear to angular using the radius.
On that AP test, can you just like use this, or do you have to show how you got that relationship in a question?
You can just use it.
Okay.
Problem is, if you don't know it, you're going to have to derive it to solve the equation or to solve the question. And you might not derive it this way and then plug things in, but what it means is you're going to have to do multiple steps in your problem to basically, in the background, be deriving this equation. Whereas if you already know it, you just jump straight to it. So it's not that you couldn't solve the problem without this equation, it's that this will make you hyper efficient comparatively. All right, so here is a nice little summary. You may want to, if you're on Zoom, you may want to screenshot this. If you're in here, you may want to take a picture with your phone if you want. This summarizes all the translational equations we've learned, or not all of them, but most of them. And also the angular equations that we've already started to learn and are going to be learning, and shows you how you can convert back and forth. So if you look at the translational column, all those red equations and variables, translationally displacement is x. Angularly displacement is theta. If you want to find x from theta, you multiply theta by r. Translationally, velocity is change in position over change in time, delta x over delta t. Angularly, it's delta theta over delta t. If you want to convert omega to v, you take the omega, the angular velocity times the radius, and you get the linear velocity. Same for acceleration. Now, at the bottom on that of these columns, you're hopefully recognize, hey, wait a minute, those are those kinematics equations we were working with first semester. The first one is the average acceleration equation. The second one is what we affectionately called the second kinematics equation. The third one is what we usually call the third kinematics equation. They've skipped the first one, which is just VVAT. Over here on the right, they've got, oh, you could just substitute, everywhere there's a V, substitute an omega. Everywhere there's an A, substitute an alpha. Everywhere there's an X, substitute a theta. And those same equations work. Now, here is where they do give you a little help. A little past halfway down on the side that's full of equations, you do see what we would look at as the second kinematics equation in angular form. And then one that's not on this slide, what we see up here as VVAT, now they have down here WEWAT. All right, so it's the same relationship, but just in angular form. So they do give you two of them, but those are the only two of all the ones we've seen today. Those are the only two that they actually provide for you. And it's kind of crazy to me because if you know this connection, those are like two of the least helpful for you to know. Because if you know how to switch A to alpha and V to omega, like you don't really need to have those kinematics equations all rewritten. But that's the way it is. So, all right, let's just do one last thing here to wrap it up. Let's just make a quick comparison to show that if you're using the linear equation or the angular equation, the math is identical. So in the first scenario, it says a car starts from rest and has a translational acceleration of 4 meters per second squared for 3 seconds. Determine the final translational velocity. Now, when we did these problems last semester, that word translational was never there, right? Because we just assumed it was moving in a linear manner, and so it made sense. Here they're emphasizing that we are talking about translational motion. We make our list of variables. It starts at rest. We're trying to find the final velocity. We're given the acceleration. We're given the time. They've chosen to use that average velocity equation, the one that's not actually given by College Board. They plug in the values and they get, hey, this car would be moving at 12 meters per second after that 3 seconds had transpired. A similar question with the same numbers, but a different scenario. A wheel starts from rest and has an angular acceleration of 4 radians per second squared for 3 seconds. So now the wheel is not moving translationally, the wheel is just spinning. Determine the final angular velocity. How fast is it spinning after 3 seconds? They've used the same equation, but with all the angular variables. They're plugging the numbers in to the same variables and getting the same numeric answer because all the numbers were the same. But in this case, this wheel is not moving 12 meters per second. This wheel is rotating 12 radians per second. All right, so just a quick summary to see basically everything you learned first semester, and the reason we spent so much time getting confident and comfortable with kinematics is if you're comfortable and confident with those equations, you use them exactly the same way now. And that's why we spent so much time really getting that confidence built up. Any questions? All right. So now, hopefully you found that worksheet we talked about at the beginning of class. We're going to take just a few minutes and we're going to look at question number 1 together. And then I'm going to have you do question number 3 in breakout groups. And that's how we're going to wrap up the class today. So let's take a look at number 1. So hopefully you all have found the worksheet. The directions here say, given one motion representation, supply the missing motion representations. In all cases, take the clockwise direction to be positive. So normally, in physics and in math, we consider the counterclockwise to be positive, but they are saying for this worksheet, we want you to do the other. I think mainly they're just wanting you to remember, you can make it whatever direction you want. They don't want you to forget that fact. So they're kind of causing you to do the non-traditional. All right, so if we look at this first scenario, if this is 0, if that's our 0 angle, it is starting at some positive position. And it is becoming more positive in those first few seconds. So let's just say it's 3 seconds. We don't really know, but just so we have sort of a number to kind of make it more tangible, let's just say in the first 3 seconds, it goes, so it's kind of like an X. Let me make sure it's clearly a positive. Hopefully that's a little clearer. We have some positive position, and then 3 seconds later, it's at a greater positive position. And since clockwise is positive, that means it's moving in the clockwise direction. All right, well, what if, let's say that this is 6 seconds, this other dashed line here vertically. So what's happening in the middle 3? From 3 seconds to 6 seconds, what's happening?
It's at rest.
It's at rest, yeah. I heard and hear these guys saying nothing. It's just sitting there. It's not rotating. All right, so what's happening in the last 3 seconds? Spinning backwards.
But more than it started at.
Yeah, faster than it was before, but in the other direction. So let's go ahead and talk about, we've kind of described it in words already. So if we were going to put this in words, we would say it starts at a positive position. Rotates, hopefully you can read my writing, rotates clockwise. So I'm just going to put CW for clockwise at constant velocity. Then is at rest. Then rotates counterclockwise, so CCW for counterclockwise, at a faster constant velocity. So another thing I could add if I wanted is there is no acceleration. All right, the velocity is always constant. It's constant. Whatever it is, it's constant. We don't know a number. Now for my motion map, they've given us a 0 position up here at the top. So if we use that as 0 instead of the traditional 3 o'clock on the clock 0, we've started at some clockwise position. We don't know where, but I'm just going to say, if that's position 0, I'm going to say this is t equals 0. And then for 3 seconds, the way I've chosen to make it 3, it's going to move clockwise. So there's t equals 1. Here's t equals 2. So there's 0 to 1, 1 to 2, 2 to 3. Remember, it's been a while, but if we have 3 seconds, that means 4 dots, right? All right, and then it's going to be constant. So this is where it's a little awkward, but I'm going to say, okay, well, here's t equals 4, and then here's t equals 5. And then, so it's at the same position. I'm trying to draw it at the same position. It's kind of hard on these circles, but, and then here is t equals 6. So I'm just mapping out my times first. All right, now we need to add some arrows when there's movement. So before we do the last segment, remember, you can draw the arrows however long you want them, but it's good to be consistent. So I'm just going to try to draw them about halfway between the dots. And in those first 3 seconds, it was moving at a constant speed. And now in these next 3 seconds, it's not moving. And then starting at t equals 6, it's moving the other direction and faster, right? So I need to make my arrows longer. So I've got t equals 7, t equals 8, and we could keep going if we want, but I'll just stop there. So that's how we would do our motion map. Any questions about the written description or the motion map? All right, how about the omega versus t? Instead of displacement versus time, what about velocity versus time, angular velocity versus time? What's the line going to look like, or what's the graph going to look like in the first 3 seconds for omega versus t?
It's going to be horizontal above the t-axis.
Okay, so I'm going to have something like that, a segment where it's going at a constant positive velocity. Evan, how about the second set of 3 seconds? What's going to be there?
It's going to be horizontal, or it's going to be on the t-axis.
Yeah. It has no velocity. So just going to be right there at 0. Sally, how about the last one? What do you think the last segment's going to look like on the graph?
It's going to be above the t-axis, but higher than the one in the first quadrant because it's moving faster.
Okay, the part about being farther from the 0 is accurate. It does, because it is faster. But if we're going the other direction,
Oh,
did you say it would?
negative. It'd be under
Yeah.
the t-axis.
Good, good. So it's going to be down here. And a little reminder, the slope of the position time graph tells you the velocity, right? So since in the first segment it has a slope of a positive value, a positive slope, the velocity will be a positive value. In the middle segment, there's no slope, so there's no velocity. In the third segment, there's a high, steep, negative slope, so a large negative velocity. All right, what I'd like you to try is skip number 2 for now and try number 3. And that's all we're going to have time for. But I'll give you 3 or 4 minutes. Try number 3, see what you can come up with.
2 and 3.
Yeah. All right. I'm gonna show you what I have here on my graph and give you a chance to compare, see if you have something similar. But before I do that, could I get someone to just describe in words what's happening here? Someone in the Zoom.
I'll do it. So it starts at a positive angle and it rotates slowly for 3 seconds counterclockwise, and then it stops for 3 seconds, and then it rotates faster counterclockwise for 3 seconds, ending at position 0.
All right, sounds good. So we've got, I didn't quite get mine back to the 0 correctly. I scaled it just a little bit off, but pretty close. So if we look at the maps, then it's a little bit harder to describe the maps verbally, but if we look at the velocity versus time, the omega versus time graph, you should have a negative velocity, which is reasonably small, and then a 0 velocity for the middle segment, and then a larger negative velocity for the third segment. And then for the motion map, you should have 3 seconds of constant slow velocity, 3 seconds of stationary, and then 3 seconds of rapid movement. And if I would have drawn mine to scale a little bit better, I would have reached the 0 a bit better with my 9, but you get the idea of the bigger and the smaller. Questions?
Do you have to label every point like t equals?
Not necessarily. I'd put the number beside it just to make sure I was counting correctly. I would put a t equals 0 by your beginning just to make it very clear where your map starts. All right.
When we start with like the placement of the from where it starts, do we have to know like the radians? So like where you started was like 7 pi over 6.
Yeah, there's really no way to know where to start it. I just looked at the previous problem. It was a positive value, but it wasn't quite as big as this one. So I just rotated further around and picked a new spot. But there's no way to really know where. You might have started at exactly the bottom of the circle. You can start wherever you want, but I also wanted to give myself enough room to get back close to that 0 by the time I was done. So I figured if I started far enough, it'd give me room.
I started from the end and went backwards so that it lined up.
I started
you
in the
started,
same place you started.
you started from where I started?
Yeah, at the radian point 7 pi over 6.
Yeah, and I just randomly picked that spot. It could be anywhere. You can technically start anywhere. I wouldn't start at 0 because yeah, we have a positive rotation. So, but we could start it, all the way around right next to the 0. Anywhere really, other than 0 would be okay. All right. Any other questions? All right, we only have a few minutes left, and I'm not going to assign anything new. This worksheet, we're going to look at questions 2 and 4 next time and talk a little bit more about acceleration. We're also going to draw in the concept of centripetal acceleration and compare those 3 kinds of acceleration that we've learned now. But there's no new assignment today. You don't need to continue this worksheet. We'll do parts of it in class over the next couple periods, as well as other worksheets that we have available. But for your assignment, just keep working on the positive physics. Make sure you get Unit 10 done by Monday night. Now you've got a little bit of information. Unit 15 might still be a bit hard to start because it's mostly on torque. You could probably do some of the vocab and maybe the review stuff, but you won't be able to get too far in Unit 15 yet until we have Monday's lesson. So after Monday, you should be pretty good to go on Unit 15 in positive physics. All right, so that is good for the day. For you guys in Zoom, if you have questions for me, feel free to stick around, but if not, you're dismissed, and take a few extra minutes for your lunch break today. And I'll see you guys next week. Most of you. See you tomorrow, Andy.
Yeah,
Thank you.
Have a great day.
Thank you, Mr. Webb.